discussion of chain rule. And for the chain rule, currently we don't have a method for finding the derivative, for finding the slope of a function like this. And what we've got to realize is that this is the composition of two functions. Now, composition of two functions normally would have parentheses. This one, if you don't have parentheses, but you can write something with parentheses, you can use the chain rule on it to find the derivative, to find the slope at any particular x value. So this is the composition of these two functions where this is g of x. This is the thing inside the parentheses. And this is f of x. This is what you are doing to the stuff inside the parentheses. And whether you know what the pieces of that composition of functions is or you don't know that, doesn't really matter. The chain rule says this: if you've got a function which is the composition of two functions, then the derivative is found by taking the derivative of the outside, don't mess with the inside, times the derivative of the inside. All right? And you see that written out in words rather than symbols down at the bottom here. All right, so let's see how this works. We've got this thing, which again, it's helpful if we write that with parentheses. Now, I've got to take the derivative of what's outside the parentheses. I've got something that has been raised to an exponent, and what derivative tells us to do when you've got an exponent is to bring that exponent around front and then decrease. Now remember, we don't mess with the inner function, but decrease the exponent by 1. All right, so if it was an x, no matter what it is, that's how we would take the derivative of a variable term raised to an exponent. Now, what chain rule tells us to do is to take that derivative of the outer, don't mess with the inner, and then multiply by the derivative of what's inside. Now, the derivative of what's inside those parentheses is 2x. So if I actually multiply this out, I think the 2 and the 2 are going to be gone. I think I'm going to be left with an x up on top, and this, since it has a negative exponent, would be driven down to the bottom. I think we're going to have an x here, and if you want to write x squared plus 1 to the 1/2 power like you see right here, that's fine. Or if you want to put it under the square root sign, that's fine as well. Either a positive exponent of a 1/2 on the bottom or the square root symbol. Okay, let's practice this one. Let's find the derivative. Now, again, this involves parentheses. And here's what's inside the parentheses, and here's what's outside. So if I'm looking for the derivative, I've got to take the derivative of what's outside. And the derivative of sine is cosine. Don't mess with the inner function. Times the derivative of what's inside. Now, you might look at this and say, do I have to simplify that at all? Well, remember, this is an angle measure. I'm not going to take that angle measure and multiply it by 2x. I'm personally a guy who likes coefficients out front, so I might write this as 2 out front. I'd probably drag the x along with it, and then write it like this. That probably would be my preference. but anything that communicates that exact same thought in an equivalent manner is fine. Now, if we got trig functions, you take a look at this and you don't see any parentheses. And so it really helps if you write that trig function raised to an exponent in parentheses if you were to rewrite what f of x is before you try to find its derivative. Now this would be the tangent of x being squared. It's not just the x that's being squared. It's not just tangent that's being squared. It's a tangent of x that's being squared. Now you can see what's inside and what's outside. The derivative. Bring that exponent around front. Don't mess with the variable term. And decrease the exponent by 1. So I've got a 1 up here. I can write it or I can just leave it blank. And then let's multiply by the derivative of what we saw inside. I don't see any reason to simplify that. I think that's fine. Now chain and quotient becomes tedious, and not any more difficult, but just tedious. Remember, I'd probably, well, I'm always going to take a radical sign and turn it into a fractional exponent. All right. So I've got to do low d high minus high, and d low is the issue. I got to take the derivative of this parentheses term. So I've got to say, let's see, 1/2 x squared minus x plus 1. Got to adjust my exponent, and then I got to multiply by the derivative of what's inside, which is 2x minus 1. Over low. Well, low is really nice here, because when you square a square root, we just have the x squared minus x plus 1. So what I've got is I've got 2 of these square roots. Minus, well, let's see, this 2, that 2, gone. This is going to be on the bottom of a fraction because it's got a negative exponent, but I can take this times this. So I think I have 2x squared minus x over this square root of x squared minus x plus 1, all over x squared minus x plus 1. It's pretty good, but I can't leave my answer as a fraction with 3 levels to it. So I guess my rule is never divide, but multiply by the reciprocal. Multiply this whole thing by 1 over x squared minus x plus 1. All right. If I take this times this guy, this is the x squared minus x plus 1 to the half up on top. This is x squared minus x plus 1 to the 1 power on the bottom. I think the bottom wins. I think I'm going to end up with this 2 up on top. And when I resolve this times this thing being on the bottom, I think I end up with x squared minus x plus 1 on the bottom. When I take this times this, I've got a minus. I think I have 2x squared minus x up on top. And I got this thing to the half times the exact same thing to the first power. When I add those exponents, I think I got x squared minus x plus 1. When I add the exponents, I think I get the 3/2 power. That is one way that that answer can be expressed. You might have a different, an equivalent form of that, and I'd have to figure out that what you've done is correct. If it's a little different, looks different, or you'd have to point out to me how they're the same. But that's what I'd end up with. All right, there are situations where we've got a double chain rule. Now, s of t is equal to sine squared of x cubed. Now remember, whenever you got a trig function raised to an exponent, you're going to rewrite that function in parentheses. You've got the sine of x cubed, which is being squared. And do you notice two sets of parentheses? And if there's two sets of parentheses, that means we've got to use the chain rule twice. Now, derivative of the outer. Don't mess with the inner. I got to bring the 2 around front. I've got to leave the term with the variable without any changes. Don't mess with it. And then decrease that exponent by 1. So there's a to the first power times the derivative of what's inside. And what's inside? Well, the derivative of this is going to require a chain rule as well. Derivative of the outer, don't mess with the inner, times the derivative of what's inside. Can you leave it like that? Well, technically it's correct. Me, I like coefficients out front, and I know that 2 times 3 is going to give me a 6 out there, and I'm dragging the x squared along. And then I've got sine x cubed and a cosine of x cubed. And that double chain rule is something that you will see oftentimes on one of the first 10 multiple choice, no calculator questions on the AP exam. All right, that is a summary of the chain rule. Take advantage of an opportunity to practice that.